Good morning. I am discussing about Carnot cycle. First of all, cyclic process. When a system in a given state goes through a number of different states and finally return to the initial stage to complete a cycle, such type of process is called Carnot process. For cyclic process, energy change in energy is constant. Energy is constant. That's why change in energy D equal to zero. Carnot cycle is a hypothetical, ideal, and reversible cyclic process proposed by French engineer Sadi Carnot to demonstrate the maximum convertibility of heat into work and ideal message to cycle is known as Carnot heat engine. Carnot cycle consists of four different operations, which is represented in pressure volume diagram is shown below. Figure schematic diagram of Carnot cycle, A, B, C, D. That is in this system, A to be changed isothermal reversible expansion. In this case, temperature is the constant, P1, V1, P2, V2. Pressure and volume changes, but temperature is T2. That's why dt equal to 0, and it is the Q2. And B2C, it is the adiabatic reversible expansion. B2, B2, B3, B3, T2, T1. T2 is the greater than T1, that's why dt equal to 0. And T2 B, the pressure and volume changes P4, B4, and temperature is the constant. That's why the dt equal to 0 is the isothermal reversible compression. D2A pressure and volume it changes into P1, V1, and temperature is T2. Adiabatic reversible compression. Isothermal reversible expansion when a cylinder is placed in a heat reservoir at higher temperature T2 and expand isothermally and reversibly from V1 to V2. For this operation, change in internal energy delta equal to 0. So heat absorbed by this substance Q equal to Q2 equal to work done W1. But from the isothermal reversible expansion of the work done, W1 equal to Q2 equal to RT2 L and V2 by V1. Adiabatic reversible expansion. Now the gas is always to expand adiabatically reversible from V2 to V3, and then the temperature of the system falls from T to T1. For this operation Q equal to 0, so work done equal to minus delta E. From the definition of the molar heat capacity at constant volume, Cv equal to delta E dt, work done equal to minus delta E. That's why minus delta E equal to minus Cv delta T, minus Cv T2 minus T1, minus Cv delta T, Cv T2 minus T1. Substituting the value of delta E in above expression, W2 equal to Cv T2 minus T1. Isothermal reversible compression. On doing the compression at constant temperature, T1 the volume decreases V2 to V3 to V4. For this process, delta E change in energy equal to 0, work done by the system during this compression, minus Q1 equal to W3 R P1 L and V4 V3. Adiabatic reversible compression on this compression adiabatically volume of goes to B2 B4 to B1 and temperature becomes T2, so work done by the system during this compression is minus W4 equal to Cv T2 minus T1. The net heat absorbed by the system equal to Q equal to Q2 minus Q1, Q equal to RT2 L and V2 by V1 plus RT1 L and V4 by V3. Q is total work done by the system, and W equal to W1, W3. Substituting this value, this to cancel, and W equal to R2 ln B2 B1, R2 ln B2 B3. From the equation 5 and 6, W equal to Q, and for additive process, TB gamma equal to constant. That's what the curve BC, curve BC What could be C T2 B2 gamma minus 1 equal to T1 B3 gamma minus 1, T2 minus T1 B3 gamma minus 1 B2 gamma minus 1. For similarly for core DA T1 B4 gamma minus 1, T2 B1 gamma minus 1, T2 B1, T2 T1 B4 gamma minus 1, B1 gamma minus 1. From 18.9, B3 gamma minus 1, B2 gamma minus 1, B4 gamma minus 1, B1 gamma minus 1. That's why B3, B2 equal to B4, B1, B1, B2 equal to B4, B3. Now the equation 6 becomes W equal to R T2 ln B2, B1 plus R T1 ln B1, B2. Now RT2 ln B2, B1 minus RT2 ln B2 by B1. W equal to R ln B2 by B1, T2 minus T1. B1, B2, B1 over B2 equal to B4, B3. And that's why the equation 6, W R2 V2 by V1, V4 over V3. So we can write V4, V3, V1, V2. Yeah, V2 and minus RT1 ln V2 by V1. W equal to R ln V2 over V1, T2 minus T1. Q2 minus Q1 RT2 ln V2 by V1 plus RT1 ln V4, V3. T2 ln B2 V1 plus RT1 ln V1 V2 and T2 ln V2 V1 plus RT1 ln V2 V1 R ln V2 V1 T2 minus T1 Q2 minus Q1 equal to R ln V2 V1 T2 minus T1 equation 12. In the current cycle, the heat converted into work is the WQ2 minus Q1. Efficiency of the work done by the current cycle equal to heat converted into work over heat taken from the source equal to Q2 minus Q1 over Q2. Q2 minus Q1 equal to RL and V2 minus V2 over V1, Q2 minus T1 over R2 ln V2 and V1. That's why neta equal to T2 minus T1 over T2. Thermodynamic efficiency of the current cycle. Thermodynamic efficiency is the ratio of work obtained in a cyclic process to the amount of heat absorbed from the source, which is denoted by the symbol neta. That's why neta equal to work obtained from the cyclic process over amount of heat absorbed, neta equal to W over Q2. Equation 4. So equation 4 becomes neta equal to T2 minus T1 over T2. From the current cycle, we have Q2 equal to R T2 ln V2 over V1 and W equal to R ln V2 over V1 T2 minus T1. Substituting the values of W and Q2 in equation first, we get theta equal to R ln V2 over V1 T2 minus T1 over R T2 ln V2 by V1. That's why neta equal to T2 minus T1 over T2. From the equation third, we can conclude that neta depends upon the temperature difference between T2 and T1. Higher is the difference in temperature between source and sink, greater will be the efficiency. If T1 equal to 0, neta equal to 1, this implies that W equal to Q2, that is entire heat is converted into absolute zero. Higher temperature complete the conversion of the heat into work may be possible, but the absolute cannot be realized in the actual practice. Therefore, no heat engine can be constructed whose efficiency is 100%. Okay. If T1 equals 0, neta equal to 1, this implies that W equal to Q2, that is the entire heat is converted into absolute zero. Higher temperature complete the conversion of heat into work may be possible, but absolute cannot be realized in actual practice. Therefore, no heat engine can be constructed whose efficiency is 100%. When T1 equal to T2, the value of neta is 0. That is, no work can be produced when engine is operated under the isothermal condition. Okay, I have discussed Carnot cycle and Thermodynamics efficiency of the Carnot cycle. Thanks for watching. Thank you for your patience. That's now. Bye bye. See you again.